Hello again. This is Math 2333 coming to you from the College of DuPage. This is the conclusion of the lecture entitled Vectors, Operations, and an Application. Again, I encourage you to be an active learner as you watch these videos. When we adjourned last time, I had you working on this problem. I hope you did it. If you did, congratulations. But we'll go through the solutions now. I asked you if A was pointy bracket 403 and B was pointy bracket minus 2, 1, and 5 pointy bracket. You find the magnitude of A and calculate these vectors. So the magnitude of A is we sum the squares of the coordinates and we take the square root of that, and so the magnitude was 5. A plus B was 2, 1, 8, enclosed in pointy brackets. A minus B was pointy bracket 6, minus 1, minus 2. This one was pointy bracket minus 6, 3, 15, and this was pointy bracket minus 2, 5, and 31 pointy bracket. Now, whenever we're talking about the set of all two-dimensional vectors, we call that capital V sub 2, and capital V sub 3 is the set of all three-dimensional vectors. And more generally, if we need to think about n-dimensional vectors, we call it V sub n, and an n-dimensional vector is an ordered n-tuple, where you have n coordinates here. You could think about having time as a coordinate or other dimensions as well, where the a sub i's are real numbers and they're the components of A. And the addition and scalar multiplication are defined in the same way as for n equal 2 and n equal 3, and also the magnitude is defined in the same way for these vectors. Vectors in n dimensions are used to list various quantities in an organized way. Here's an example of P, where P is equal to pointy bracket P1 through P6 might represent the prices of 6 different ingredients required to make a particular product. 4-dimensional vectors, and there you see the T happening, are used in relativity theory, where the first 3 specify a position in space and the 4th represents time. We will talk about some of these as we go forward. Now, we do have several properties of vectors. If you add vectors, it doesn't make any difference which way you add them. So A plus B is B plus A. It is also associative. A plus parentheses B plus C is parentheses A plus B plus C. If you add the 0 vector to a vector, you get the vector you started. Every vector has an additive inverse. And we have distributive properties that look like this and this with respect to scalar multiplication. So far, we've only talked about scalar multiplication, and this is how scalar multiplication works as well. And if you take the scalar 1 times a vector, you get the vector itself. Now, those things are actually quite easy to prove, because what you can just do is list them as components. Here's A plus B. So it is this pointy bracket vector plus this pointy bracket, which is this. But by properties of real numbers, this A1 plus B1 is the same thing as B1 plus A1, and so on and so forth. So you switch them, and you can see that that's the same thing as B plus A. Now, there are 3 vectors in V3 that play a very special role. And so if we let I equal the vector pointy bracket 1, 0, 0, J equal pointy bracket 0, 1, 0, and K equal pointy brackets 0, 0, 1. Those are called the standard basis vectors. These each have length 1 and point in the direction of the positive x, y, and z axis. So here in 2 dimensions, this is the vector I, this is the vector j, and in 3 dimensions, this is the vector I, this is the vector j, and this is the vector k. Now, the reasons they are called basis vectors is any vector can be represented as a linear combination of these vectors. And let's see this in 3 dimensions. If A equals A1, A2, A3 in pointy brackets, then we can see that A then also is equal to A1 times pointing bracket I plus A2 times pointing bracket J plus A3 times pointing bracket K. So any vector can be expressed in I, J, and K. For example, this is the same as this vector. In your physics classes and engineering classes, sometimes the I, J, and K notation is used instead of pointy brackets. And it works the same way in 2 dimensions. And here is showing that yet again. Now here's an example I would like for you to work. So if A is equal to this and B is equal to this, what I want you to do is express the vector 2A plus 3B in terms of I, J, and K. You know what to do. Let's see how you did. If you did this problem, congratulations. If not, please follow along. You add the components. This is 2 times this vector plus 3 times this vector. Notice that these are 3-dimensional vectors, even though this only has components in 2 directions. You collect like terms, and you end up with 14i plus 4j plus 15k, or this could also be written as pointing bracket 14, comma 4, comma 15. End of pointy brackets. Now a unit vector, and we've already talked about one, which is the i's, j's, and k's. A unit vector is a vector whose length is 1. So for example, I, j, and k are all unit vectors. But in general, if a doesn't equal to 0, the vector a does not equal the 0 vector, then you can find a unit vector that has the same direction by dividing by the length of a. Because if you look at this, and we divide by the magnitude of a, then if we take the magnitude of this, we can pull this out of the magnitude, and the magnitudes will cancel, and so it's 1. In fact, here's a proof of that. Okay, so the magnitude of u, where u is equal to c times a, and c is 1 over a, is equal to 1. And so a lot of times the problem I will ask you is to find a unit vector in the direction of this vector. So use this property. You know what to do. Let's see how you did. So the length of this vector, we use our formula for this. We get 3. And then we know that this, all I have to do is take the vector divided by the length of the vector, and I get that this is the unit vector in the same direction. You see, so this tells us what direction the vector's going in. So we talk about magnitude and direction, and sometimes we want to decompose vectors into that way. A little bit of history. Gibbs was the first one to start talking about vectors, but he built on work by the Irish mathematician Hamilton, and this was in turn used by Maxwell and Heaviside to do electromagnetic theory, and we might talk a bit about that at the end of this course. But now let's do a simple example. Vectors are useful in many aspects of physics and engineering, and later we'll see how these describe the velocity and acceleration of objects moving in even space. But here we look at forces. A force is represented by a vector because it has both magnitude, measured in pounds or newtons, and a direction. If several forces are acting on an object, the resultant force experienced by the object is the vector sum of these forces. You learned this in your physics class, or perhaps you're learning it now, but that is some physics that you could know. So here's an example. A 100-pound weight, this one, is hanging from 2 wires like this, and these wires are holding this weight up. You think about this as a picture frame or something that's hung this way. So we have T1 is a tension this way, and T2 is a tension this way, and you see what these angles are. And so what you want to do is find the tension forces T1 and T2 in both wires and the magnitudes of the tension. So you're finding the magnitude, you already know the directions. So you want to find out what are T1 and T2 as vectors. You know what to do. Let's see how you did. Okay, so first of all, we want to look at our diagram again, and we realize that since the ceiling is parallel to the ground, this angle is 50 and this angle is 50, And so what we can do is we can consider T1 and T2 to be components. Now, T1 and T2 balance the weight because it's not accelerating downward. In fact, it's staying right in place. So what we really have is that T1 plus T2 as vectors is minus the weight vector, which is 100 joules. Now notice that we're taking the weight to be we're taking that to be a negative component. So a negative and negative is 100 joules. Or you might think that these are pulling up while that is pulling down. So T1 plus T2 has to be 100 as vectors. And that means if we take the, if we talk about the magnitudes, then that means that since these are the tensions, then that this component, there's a component of T1 pulling up and a component of T2 that is pulling up. And so here we use those angles. And so we have these are the components of T1, T2. This is the magnitude of T1 times the cosine of 50 degrees, and this is the magnitude of T2 times the cosine of 32 degrees. And in the J direction, these are the magnitudes, and that has to equal 100 joules. But you see, two vectors are equal if and only if their components are equal. So this I component, since it's not moving to either side, has to be 0, and this one has to add to 100. So you see, we have two equations and two unknowns that we can solve. Now, the arithmetic is kind of heavy, but what we're going to do is we're going to solve the first of the equations for the magnitude of T2. So we throw this to the other side and divide by that cosine. And we get that this is equal to 100. And you see that the only thing now that I have, the only variable I have now is the magnitude of T1. So that I can factor the magnitude of T1 out of there, compute what this number is, and then I can solve for the magnitude of T1. I get that that is 85.64. And then I know that the magnitude of T2 is this expression. So I substitute in, and I find out that the magnitude of T2 is this. So you see, we know that these in the I and K directions, that this T1 is going to be this number, and T2 is going to be this number, because what I can do is I can add the components that I have here. This was T1 and this was T2. So if I know the magnitude of T1 and T2, I can write what this is, and I have solved this equation. So I know this is T1 and T2. Now I was rounding things off, so these are approximate, but engineering is often about approximate problems. This is a very common kind of problem that you might expect to be able to solve. In closing our lectures about vectors and an initial application, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.